Hi, I'm Antonio Sala, and in this video we'll discuss how to animate a simulation of a 3-mass 4-spring system which we modeled in previous videos. This was the system. Input was the displacement of the rightmost end. These were the differential equations, all masses and spring constants being equal, and this was the normalized matrix form state space representation. We can copy matrices A and B from the state space representation into MATLAB, and we can select an output equation with matrix C consisting on 3 rows, 3 outputs that extract states 1, 3, and 5, which correspond to the 3 positions. If we give some initial conditions and some input, in this case 0 input but non-zero initial conditions, that's called free response, we can simulate it either with a generic ODE for 5, in which we simulate the state equation from a given set of initial conditions, and later on in the output equation, in this case we just extract the first, third and fifth columns from the simulation results. Or alternatively, we could use a specialized linear simulator routine in Control System Toolbox by building a state space ABCD linear systems and using the linear simulator LSIM, giving initial conditions and a set of time instants and the vector of inputs at those time instants. As both simulations gave basically the same result, I am setting this ODE test to false because only one of the ways of simulating is actually needed. So how do we animate this? Well, we'll briefly outline the code because my emphasis is on modeling and simulation and not on graphics and animations in advanced MATLAB. So you are free to pause, stop the video, or look at the source code, which I attach in the video description. So first figure, I plot the time response, the time and the positions with respect to time. And in figure 2, I plot the animation. Spring X and spring Y is just the plot of a set of segments that resemble a spring. Here we have it, so I will draw it longer or shorter depending on the length of said spring. And capital N is 8,000 samples I am simulating. I will simulate only 1,000 of them. I will skip every 7 out of 8 frames for this to run faster. And I will animate either horizontal or vertical vibrations. So in the horizontal animation, I will use some plots to draw the springs. For instance, this line draws the leftmost spring. The length of the spring depends, of course, on the position of the first mass. Of course, we need to put some constants because, in the incremental simulation, the operating point and the things are sort of centered in 0, but in the actual animation, the spring starts in -3, but its final end, it's another position, in absolute coordinates. So I played with these constant numbers until I got a nice looking figure. The second spring's length depends on the difference of positions of mass 2 and mass 1, and so on. You are invited to have a look at this code to see how it works, or even change some numbers to see how springs get drawn at different places. 0, 4, and 8 will be the equilibrium position in absolute coordinates. In my animation, I will draw a vertical line to pinpoint these equilibrium positions, which are the origin of the coordinate system in incremental units. Then the patch command draws a polygon with a given color, and I will use this patch command to draw the left and right walls as well as the 3 masses. these rectangles here. So that will be the longitudinal vibration, and well, the transverse vertical up-down vibration will be also carried out via some patch commands to plot the masses oscillating up and down. Now it's the second component, the vertical displacement, which depends on the simulation results. So I will draw all this to see the simulations. As I said, look into MATLAB's documentation and play a bit with the code in order to understand all this. The important thing is how simulations feel when we see the animation. So we'll first see this zero input, non-zero initial conditions, free response. Here we have the upper plot is the time response, the 3 positions as a function of time, and as the system is stable, it loses energy, and at the end, the incremental displacement ends up being 0, which of course means that the actual masses end up stopping at their equilibrium positions. So this is the animation of the longitudinal vibration free response. The same simulation data can be used for an animation of a transverse vibration. If I set horizontal plot here equal to 0 and I execute again. So let's see. Here we have the upper figure is exactly the same. And the transverse vibration, look, the input is not moving, it's free response, and well, movement gets closer and closer to 0 until it stops if we leave it simulating for long enough. We will now simulate force responses. For instance, 0 initial conditions, but sinusoidal input. These are indeed some resonances, high amplitude solutions, but computing the resonant vibration modes is out of the scope of this video. We just wish to have a look to the animations. So if I simulate this first vibration mode as a horizontal animation, I get this. You can see that in the first 30 seconds, we have sort of oscillations of increasing amplitude. And after 30 seconds, we get what's called the stationary steady state sinusoidal response. And indeed, the response are 3 sinusoids with a given amplitude and phase shift between them that in this case, it seems that the 3 masses move in phase, roughly. There is a small phase difference, but not really significant. As you see, all of them move, all of them left, all of them right. If I animate it as a transverse vertical vibration, simulation data are the same, but the animation looks different. This is the first vibration mode. All the masses move in the same direction. And we'll see other vibration modes. For instance, the second vibration mode occurs at roughly double frequency. I increase a little bit the amplitude as well, so you can test by yourself what happens with changing frequencies and amplitudes. So if I simulate now, we get the second mode of vibration in which the central mass moves with a significantly lower amplitude than the first and the third one, and the first and third move in opposite phases. Steady state sinusoidal regime. What would be, steady state alternating current if this were an electrical circuit, is reached in sort of 35 seconds. Then the last mode of vibration is this one, in which again in 35 seconds we get a steady state, and now it's the central mass which moves in opposite phase to the left and right masses, and this is the third forced vibration mode. Of course, input does not necessarily need to be sinusoidal. We can put whatever input we wish, but these particular sinusoidal inputs are of importance in vibrations, in alternating current, in electrical circuits, etc. But of course, if I change the sinusoid to a cube of a sinusoid, well, no problem with that. And as you can see, it sort of stops in the middle, but okay. At the end, the output looks sinusoidal because, well, the high frequency harmonics somehow have no significant influence in the overall vibration. So let's summarize. In this video, we outlined the code to animate a simulation in order to better understand physically what the solutions of ODE45 or LSIM did mean. We simulated free response, forced response with sinusoidal input, the so-called resonant vibration modes, and last we simulated a non-sinusoidal input, just to illustrate that really input can be arbitrary. So we finish with this. Thanks for watching.